Okay, good morning, everybody. We'd like to start this workshop today, the Keep It Cool workshop. My name is Sander Smit. I'm working for Art Solution and for the High Quality Project. Our host facilitator, my fellow facilitators, Fausto.
Hello, I don't know whether you know him, Fausto aside from Comet, and if you remember, the True Culture Waste is part of the Smart Energy cluster, so it's a cluster inside a cluster. So we're going to talk today about the projects, and I hope you will mention not just what we can find on the website, which is accessible to everyone, but maybe some sort of problems you're finding, or some sort of new solutions, or something interesting. Okay, so last week we already had a webinar, if you remember. Maybe people may not know about that, but in this case, I would like to have some more interesting insights about the evolution of the projects. So with that, Sander, who is the first speaker?
Yeah, I'll just show a little bit the agenda. We have 10 projects, system projects that are sharing the results. Each presenter has 10 minutes. I will do timekeeping. I give a 2-minute heads up when time is running up. 2 blocks. First block is a little bit more focused on data centers and cooling solutions. Second block is more broader industry and cooling solutions. And in between, we have time for discussion, moderated by Rosanna. With that, I want to start. If there are no questions at this stage, I guess not. Good. Then I give the floor to Rosanna.
Thank you. Great. Good morning. Welcome in Milan. I hope you were enjoying it. And I'm Rossano Scoccia. I'm based here in Milan, and I'm an associate professor in Politecnico di Milano at the Department of Energy. And the coordinator of High Quality is my colleague Marcello Aprile, and he will come here in the afternoon. And I present you this project. The motivations, I think I don't have to say to you the motivation to be here, but yeah, briefly, let's say our project is more on medium, small server rooms and not on big data center. So, indeed, most of the server room in Europe have around 25 racks. And in this High Quality project, we have a pilot with 32 racks. And, they are very energy intensive. Right now, in these small rooms, you don't have a proper design, proper system. So often you use rack systems that are not efficient at all. And you don't recover and you don't exploit what is the waste heat. So in our High Quality project, that is a European project of 3 years, now we are in the middle of the project. We are trying to tackle it from a different point of view with the digital solution, but also hardware solution, and also then deploy it and exploit it in terms of standardization. So the consortium is made by 9 partners, actually from 5 European countries. So from Italy, Politecnico di Milano, Department of Energy, CNR, where Valeria works, R2M, where Sander works, and then we have IMP from Serbia, Sorption Technology from Germany. They developed the adsorption chiller, that is one of the technology. And we have Comet with Fausto, that is here. IDP, we have some colleagues around from IDP, and BDTA, that is the Building Digital Twin Association. We will talk about Symbot, and there are other sessions where they talk about this approach. And then we have also the European Innovation Market, based both in Belgium. So the objectives are 4. The first one is digital, to build the building digital twin, and then to provide it as a product as a service. This is our idea. And this digital twin is based on this approach of easy modeling, having these symbols, that is a kind of library where you find components and easily you can build your digital twin. This is the first pillar. The second one is about the hardware, developing a rack integrated adsorption chiller done by Sorge, so exploit the waste heat from the server in order to run the thermal driven cycle. Then we will test it both in real operating condition in our server room in Politecnico. So the pilot is our server room in the Bovisa campus, where is also my office. And we will also test in laboratories. We have a laboratory, double climatic chamber where we can test heat pumps, and we will do it. And last but not least, there is also the standardization part that is very important in order to have a good replication potential of what we are doing. Here you see this complex chart. I will need like 20 minutes to talk about it in detail. So yeah, maybe we can discuss it further during the discussion session, or you can have a look to the presentation, or you can read the paper that we presented in CONAS, in the Building Digital Twin International Congress in May. We published it and we explain it very well. Here you see a lot of acronyms. So briefly, I try. This is the physical asset, so the energy system, where we have the data center, and the idea is also to have a waste heat recovery system of this heat from the data center in order to heat a nearby building, BL26. And then this data then from this physical model, we collect monitoring data. This monitoring data go to a database, and this monitoring data are used also by a software in the loop approach. And this software in the loop seal, we have an MPC, model predictive controller algorithm, in order to optimize the control trajectory of the overall system, both the data center and the waste heat recovery system. Then we have another part that is the part about the modeling, the SimBots. So we have a digital replica of our system where we can see how the system should works in theory. And so then comparing what is happening in reality and what should be, we can do this software modeling tracking system where we compare the data and we understand if the system is working well or not. So which is very useful both in the commissioning phase, in the initial phase of this complex system, and then in the whole life of the system in order to minimize the performance gap that we know often happen. And then about the MPC part, I admit that we put here a second control. You know that data center are important system. They cannot have failure. They cannot have issues. In this data center in Polytechnic, we have administrative tasks and research tasks, and all the administrative part of Polytechnic cannot have issues. So for this reason, right now we put, let's say, a filter between what the model predictive control says and what when it's actually applied. So we have a human control right now, but in the future we can think to remove it. Here it's more or less the same, simply looking more from the physical point of view, how it works, what are the different systems that we are using, the different technology that we are using, but it's again about what I said to you before. While here we move to the second pillar, so the development of a rack integrated absorption chiller. Here Sorge we developed a new cycle. It's a little different compared to standard thermal-driven absorption cycle. And the cool idea is to have this absorption chiller rack integrated, so directly in the rack. So as you can see here, it uses as high temperature source the heat produced by the computers, and then cool it down, and then of course it needs another circuit for the medium temperature heat discharge. And we are working on it. They are working on it hardly. They developed the first prototype. They had some issues, and now they are working with second prototype, and then we will test it in Milan early next year. This is the plan. While about the testing of this, we will do it in, as I said, in Bovisa campus. This is our server room. There are 32 racks. Last year, we were using it with computer not super new, so with 100 kilowatt of electric power. Now we are replacing it with much newer computer, with much higher power density. So now we are reaching 200 kilowatt of power, but we have to throw away. The maximum capacity of a cooling system here is 300 kilowatt. and we will reach it very soon. And yeah, it's based on two islands. So we have a hot island that is inside this door, while all the outside it's cold. And these are the chillers that we use. So we have two large air-cooled chillers, two just for redundancy. So one is working, the other not. And if one is broken, we have the other one. And then we have also an emergency generator, because in data center, it's very important. And last but not least, we have the BL26, that is the building that we heat with the waste heat recovery system. The waste heat recovery system is based on a water heat pump. So we take we preheat the water thanks to the discharge heat from the data center, and then we send to a water heat pump in order to increase the level of the temperature, and yeah, provide it at around 58 degrees C. And let's see if we can reduce it a little. So, in conclusion, we are optimizing the cooling system, and in this optimization, we are doing different things. I didn't say to you before, but right now we are changing the so-called in-row coolers, that are a kind of fan coil that we use in order to cool down the room, with higher effectiveness heat exchanger in order to be able to increase the temperature of the chiller loop. Then we are working on the strategy about the use of the free cooling and the use of the compression cooling in the best way. We have Schneider as provider of the whole system. They have already what they call intelligent free cooling, but we see that there is space for improvement of this. And moreover, as we are adding a heat recovery system, we have to take care that instead to free cooling, we should take this heat and not give it to the air, but give it to the building BL26. So we have to play a little with it. And of course, in this way, we can improve the seasonal energy efficiency ratio of the system. And then we are working on the molecular heat control, that is a very cool technology for off-design condition, and in order to work in a dynamic system, so basing our control action on an horizon of around 3 days, based on some of the weather condition, etc., etc. Then the second step is the waste heat recovery. BL26 right now it's using gas boilers, so doing this we can reduce a lot the CO2, and we saw that it's also good economically. So the OPEX reduction makes sense to do this CAPEX increase. And in the future, we also plan to couple it with the district heating network that we are doing in Bovisa. And of course, we have also the absorption cooling that we could use as heat source. Thank you. That's all. And yeah.
Perfect. Yeah, we do questions in the discussion session. Thank you. Very nice. Next, thunder project presented by Matteo.
How much time do we have? 30 minutes.
I'll give you 2 minutes. Perfect.
Good morning, everybody. It's a pleasure to be here and with you, and of course, thank you for the invitation to this occasion. And my name is Matteo Porta. I'm working in Vena Consulting, and I'm the coordinator of the other project. And I will show you something about this. And the title of my presentation is Waste Heat Recovery from Data Centers, and coupling heat on wheels solution with thermochemical seasonal storage. And the objective from the call we answered from the European Commission was to develop solution for long-term duration storages. And so we presented this solution with thermochemical materials for seasonal storage in order to understand how they could work in comparison with the standard storages like water storages. And then we found some difficulties, because now I'm going to show you with the connection in our demo site between the data center and the direct connection between the data center and the district heating network. And so we found a way to overcome this problem with this hit-on-wheel solution that I will try to explain during my presentation. So the main aim of this project, as I said, is waste heat recovery from a data center, and to couple the data center with the district heating network via a seasonal thermal storage that in this case is thermochemical storage with thermochemical material. And in any case, a direct connection was foreseen since the beginning. And then, of course, one of the main other objective was the cooling server to the data center. So as you can see here, the main focus was to develop the thermochemical storage coupled with an high temperature heat pump in order to increase the temperature and match the temperature of charging and discharging of the thermochemical storage with the temperature from the data center from one side and the district heating network from the other side. We are developing advanced control logic like MPC that was mentioned before, but then we needed to modify a little bit due to the change of configuration. We are testing advanced material for the thermochemical storage for increase the efficiency and the effectiveness of the thermochemical storage. And then there are other important objectives related to business models, stakeholder engagement, and sector coupling. Here you can see the list of partners. So we have this demo site that is a data center with a district heating network. The data center is managed by Abeliksoft, a software company in Bulgaria. And Veolia is managing the district heating network again in Bulgaria, in Varna. And then there are a lot of other companies that are involved in the project. So the main objectives are listed here. So apart from the waste heat recovery and the seasonal storage, we are also, testing some systems in order to increase the effectiveness of the storage, like the solar-driven ejector thermocompression vacuum system in order to create the vacuum into the test cell, into the heat exchanger for the thermochemical storage in order to increase the efficiency, as well as some other devices that we are introducing in order to increase the capacity of the system. This is the final layout as it is now. We are in closing the second year of the project. The project will last for 4 years, and so we are quite in the middle. And we are closing the design phase of this layout. And as you can see, we need to move from direct connection to an heat-on-wheel solution. So the heat is moved from the data center area here via a PCM, so phase change material, not TCM. The TCM, the thermochemical material, is here. Initially, as I was saying, was planned a direct connection between the data center and the district heating network. But at some point, very early in the project, the district heating network in Veolia told us that it was no more possible to direct connect the facilities. And so we need to solve the problem. And we find a solution that has been accepted by the coordinator, Rina, of course, and the officer. After an amendment procedure, and now this solution has been accepted, and this is the status that we are designing in details. So basically, as you can see, we are charging a PCM, and this is done in one per season in order to charge the TCM. Then that is the seasonal storage that we would like to test. But also, we would like to test also a more frequent connection, like simulating a direct connection. Of course, it cannot be a direct connection, but the idea is to even exchange heat frequently, daily, weekly. This is something that we are discussing. So the PCM is moving the heat from the data center to the district heating area, and then the heat is heated up in terms of temperature in order to charge it and then discharge the thermochemical storage that needs to be elevated again in temperature in order to feed the district heating network. Of course, this is not the initial solution, the direct connection of 3 minutes. Okay, sorry, I need to speed up. So this last part of the slide means that this is the sort of value chain of all this part of the system. We divided it in different components in order to understand who is taking care of what. As you can see here, there are two main boxes to understand that the data center. Is it true that system provider, a service provider like Veolia could provide cooling to the data center, but the data center owner, that is Abilix, want to have all the possible management of the cooling by their own. So they don't want it to be that anyone could interfere in the management of the cooling. So we are discussing a lot on this part, just to say this. Then, from the technical perspective, we are testing a test cell. This is done by Stiltec, an Italian company based in Puglia. And the test cell is now a prototype that is testing the heat and hydration and dehydration of the thermochemical material. And this is a prototype that we are moving actually from them because they built them to Unifi, University of Florence, in order to test where here they have a test bench where they are simulating the conditions of heating, cooling, so they can connect a high temperature heat pump that is coming from another Italian company in order to test all the condition in their lab. Of course, there will be a lot to say, but only 45 seconds are remaining. Then this is their facility again in Unifi, University of Florence. They are testing several materials, how they perform when hydrating and when dehydrating. And this is a sort of summary of where we are now. So we are testing TCM 71, that is calcium chloride with a vermiculite matrix to host the calcium chloride. Then they tested the performance of this salt together with vermiculite, and they found nice results. But then, due to some problems in hydrating and dehydrating and heating up and heating down the vermiculite, we are moving to silica gel. Silica gel as a matrix that can host the salt, that is the thermochemical material. And we are finding that the silica gel solution, sorry. Okay, I'm quite close to finish. And they are finding that the silica gel as a gnostic matrix could work even better than vermiculite. And to close, yes. But this is just to mention the design phase. We are dividing the system into several components. This is quite similar to the other slide. Just to say that we are also designing the control part that is quite important to define as objective of the project. Thank you, and see you later.
Thank you. Thank you, Matteo. Next is moderator project presented by Jan. This there was up and down. You should be good. Perfect, thank you. I'll sit there like this. You have 2 minutes.
Good. Yeah, good morning, everyone. Thank you so much that I get the chance to present our Horizon project moderator. My name is Yannick Graben. I'm from the Competence Center for Thermal Energy Storage in Switzerland, so in Lucerne, at the Lucerne University for Applied Sciences and Arts. To give a quick overview to the moderator project, so the way we work with data centers is really we focus all on the waste heat recovery system. We work with an immersion cooling system, where the goal is really to achieve a system with the highest possible temperature without having kind of a certain amount of thermal degradation of the server racks. Then we kind of use the waste heat, this intermittent availability, store it in a newly developed phase change material that I will go deeper into after. And then the third and the last part is actually also setting up the insulation material for this storage system. Then what we also look into is different case studies that we have within the project. So we look at different locations. We determine now 3 locations with different server units or different data centers. And there we really look into how we can use this waste heat that is stored in these phase change materials for other uses. So in industrial applications, greenhouses, and so on. Exactly. Quickly looking into the consortium, we are distributed all around Europe. The pilot, or one of the pilots that is planned, is in Greece. So our data center provider that also developed now their own immersion cooling system is Synapsicom. They're located in Athens. So this is also where our first pilot will be built. Then I said HSLU and COBA, we work together at development of the phase change material and also the storage system actually, so how to get the heat in and out of the materials. Then we have Sintef in Norway that is doing some simulation works on the temperature distribution also in the immersion cooling unit. So how does the temperature affect the server? How can we achieve as high as possible temperatures of the dielectric fluid in the servers? Exactly. And what I will go into now real quick is something that we are mainly working on, so really into the material studies that we have done. And we're also, it is a 4-year project. We're also now halfway into the project, actually, with the first report that we had to deliver at the end of last year, which was on the material development and the testing of these new phase change materials. That should be applicable within this temperature range of, let's say, 40 to 60 degrees, that kind of are allowed to operate an immersion cooling unit in. Then I will also look a little bit into the next task that we have to submit at the end of this year, actually, which is then really the system design. So how do we design the immersion cooling unit connected to the PCM storage and how it is operated? So we have actually developed 3 materials within the project, within this target temperature range. We work with salt hydrates mainly because they're cheap. They're not toxic, so they're available. Basically, they're food grade, so they're also used in many food industries. We have now set 3 materials. In the end, we focused mainly on this PCM 58 at a phase change temperature of 58 degrees C, and that is PCM 45, where we have now over 1,000 cycles tested of the materials within the testing unit I will show after. Real quick, in the end, we selected the PCM 45 for our first prototype because the phase change temperature is just low enough to be charged with a server unit, because there always, of course, we have this trade-off. If we increase the temperature in the immersion cooling unit, the servers will run less efficient. But of course, we cannot charge our phase change material. So one of the first tests you've actually done is in this 3-layer calorimeter. You see there the enthalpy distributed over the temperature. and you can see this nice enthalpy peak at around 49 degrees, so exactly what we are looking for in a phase change material. Then the second step, how we test this material. This is a setup which is the so-called mini cell setup that was also developed within this project. The goal really here is to test PCMs at larger volumes, because everyone that has worked with scale-up production of phase change material knows this. You can test the material in small batches, but as soon as you go into several liters, it behaves totally different. So this has a volume of around 0.6 liters, and what you can see there is really tests all the way on the left is fully crystallized, then semi-charged, so semi-liquid, say 90% charged, and then 50% discharged again, so the crystallization process. And here it's also really important to observe visually how the material behaves. So do we have segregation? So do the additives settle down in the materials and all of these processes? Then some quick results on the performance of this mini cell. The way this is operated, we actually have a water circuit that runs through this aluminum body and then heats up the material with it inside the aluminum body, and also we can use the cold water to discharge it again. There's no direct contact between the water and the PCM, so it's all within this aluminum body. And on the left, you can see the inlet temperature of the water, and on the right, the discharge temperature then, with this nice plateau that we are looking for, exactly for these PCMs. And the most important thing here is actually the theoretical stored energy over a large number of cycles. That here are shown around 130 cycles of these 1,000 that we have done within the mini cell. And you can see there really that the energy stays quite constant, so the energy that we were able to discharge stays quite, doesn't degrade. Yeah. Then the next step, what we're going to do with this material, so together with Cova Thermal Solutions, we actually developed a larger storage unit, which is this so-called compact cell here. It's a 120-liter unit, and within this targeted temperature range, we are able to store around 12 kilowatt hours of thermal energy. One of the main goals also of this moderated project was to have a scalable product. So you can connect as many units of that system as you want. You can integrate different PCMs. Basically, it's a rather simple unit. In there is in the PCM, it's an embedded heat exchanger, finned heat exchanger with two circuits, so a charging and discharging circuit to then efficiently charge and discharge the material. We have now also built the first pilot. The one picture you see there is actually a pilot that is in a multi-family building that was now operated for one heating season already. So it started to operate already last winter, just really this long-term testing. Then to sum up real quick, so we have achieved now two materials within this temperature range with a stability over 1,000 cycles. But of course, this has to be tested also close to the application, because now all of the cycles were pretty similar. So we have different, similar temperature distributions, similar kind of boundary conditions. The mini cell that was developed proved as well its test setup before then the real scale up to larger material volumes. Then it's really important to point out the importance of this PCM testing as close as possible to the application, so larger volumes and different charging temperatures like semi-charged systems and all of that. We used actually eutectics to depress the melting point of the phase change material. I will not go deeper into the material composition because Cova has still a patent pending there. Yeah, and it's just like really important to optimize the melting point for this immersion cooling system to get as close as the operation temperature, but still not have thermal degradation of the server units. And last thing, actually, I would like to use this chance as well to point out that we have our symposium coming up that I would like to invite you all. Focusing on thermal energy storage. We're growing every year. We have now around 500 participants from industry and also from research. yeah, it's in beautiful Lucerne, so come by. Would be nice to see some of you there. Yes, thank you so much.
Thank you. Perfect on time.
What's the question?
Yes. Sometimes you request something.
Yeah, you don't do it all.
So next project is the Parameditos project presented by Lorenz. Just can click through. There was a button for now.
Yes, I just must. All right. Okay. Thank you very much. Good morning, everyone. I'm Lawrence Payonga, and I'm presenting Parmenides, plug-and-play energy management for hybrid energy storage. But I will focus more, among other things, about the flexibility activation through hybrid energy storage and trade-off management. I come from KTH Royal Institute of Technology from Stockholm. So you can see here, it's the project name, plug-and-play energy management for hybrid energy storage. And it's a project that is coordinated by Austrian Institute of Technology in Vienna. And other partners include us, KTH in Sweden, Denlab in Germany, Energienetz Steiermark from Graz in Austria, Trialog from Paris, Experiencia from Switzerland, and R2M, and then MAPS Group from Italy. And as you can see here, the project is named after the Greek philosopher Parmenides, as the founder of ontology. And it also makes sense that the first objective of the project is to develop an ontology for energy community with focus on electricity and heating domains. So this ontology is used as a knowledge base for objective number 2 for an energy management system that uses this as a knowledge base to support use cases related to energy communities and hybrid energy storage, and of course, to make sure that there's secure and reliable data exchange. But what differs is in the application, and I will focus more on the flexibility activation, particularly in the Swedish pilot. So, okay. Yeah, so there are two pilots here. We have the Austrian pilot and the Swedish pilot. In the Austrian pilot, the focus more is on the on reliable grid behavior that is connected with an optimal operation of the battery energy storage system that is in Graz. So we have two municipalities in Graz that are involved here, the Gassen and Heimschuh. And then the EMS for Hess, the EMS that's developed, is integrated with the grid capacity management software that was developed by AIT. Whereas for us in the Swedish pilot, the main objective is to assess the flexibility potential of residents in a multi-apartment building in KTH. This is called the KTH Live-in Lab in Stockholm. And we demonstrate that by looking at how electrical and thermal energy storage systems put together can provide flexibility at different timescales. And this flexibility strategy will be the main thing that I'm going to talk about in the next few slides, which accounts for different constraints and preferences and being able to provide flexibility without sacrificing any of these objectives too much. So I think I better show you more about how it works. It's not very complicated. Under normal conditions, the preference is set. So like you have an energy community and its members setting their main priority, their optimization objective. So this optimization objective from the user's perspective can be maximizing comfort, minimizing cost, or minimizing environmental impact with CO2 emissions equivalent as the proxy indicator. So under normal operating conditions, the algorithm, the control strategy will pursue that preference, that objective. But then the flexibility strategy kicks in once a flexibility request is received. So this can be in the form of a flexibility signal coming from the grid or the aggregator, or the grid or the aggregator where the energy community is connected to. So when the flexibility signal is received, then the trade-off calculation happens, and it informs the user or the energy community what will be the trade-off in complying to such a flexibility request and how much of the flexibility requests can be responded to without sacrificing the objectives. So essentially, this is flexibility at the activation use case to examine the trade-offs among competing or complementary objectives. And our main method to develop this strategy is called trade-off exploration exploitation. And one of the most, perhaps the most popular algorithm to implement the trade-off exploration exploitation is called reinforcement learning. And I'll show you some brief results after this one. But after running all the simulations and training the algorithm, we are going to implement it to this hybrid energy storage system test bench that we built at the Grande Lab at the Division of Applied Thermodynamics and Refrigeration at KTH. So this test bench includes two types of thermal energy storage. We have sensible heat and latent heat. So latent heat thermal storage uses a PCM. And then sensible heat is just water. And then we have a load emulator there, and we use the data from the Levin lab to as an input for the demand that will be emulated by the emulator. So some quick results from the first version of the algorithm. So what we saw was an adaptive control during this simulation, meaning that the way that the controller behaves really depended on the conditions at that particular moment, where there were flexibility requests that if responded to would be coincidental with a high price peak, then maybe it will not do it, or it will do more because like the prices is lower. But if it will have an impact on the comfort, then it will not do it. And then, I will not show you the detailed graph of that the results of the adaptive control, but I want to show you the trade-offs here. So you can see here the three colors. The green one is for comfort mode, and the red one is red or orange is pursuing an economic mode, and the blue one is when a flexibility request is received. And you can see here that in the comfort mode, you have a very narrow comfort deviation band and very close to the set point, which is 20. And then you see when it went to economic mode, then the average temperature has deviated somehow, and also like the comfort band has increased, the temperature band has increased. And when in flexibility mode, the range of temperatures have broadened, and also there, like in two of the three cases, it's the cost is somewhere in between. So, but then after this one, the next step is to implement. So this was tested in a simple simulation environment with a simple building, and now it was done to have a proof of concept and to see that how can we actually measure these trade-offs. And the next step will be to implement that algorithm on the test bench using multi-apartment data. So, but then apart from that, other project results. So the Parmenides Energy Community Ontology has already been done. It was finished last year, and it's now being used by the EMS for HES developed by MAPS. And integrated in Austria with the grid capacity management. As you can see here, these are the forecasts, and no, this is the actual data from the grid, and this is how the EMS for HES was able to plan the state of charge of a battery, accounting for the outputs of the grid capacity management. Now, so for the key learnings and recommendations. So we assert and we have shown that there are trade-offs. I think we need to accept that there are trade-offs among optimization objectives, and that we have also shown and will continue to show that these can be measured and managed. We want to measure them and show these information to stakeholders, because we are also aware that participation of stakeholders in flexibility provision relies upon the assurance that okay, this is the amount I'm willing to trade off so that I can contribute. Because most of the time, flexibility provision is only framed from the perspective of the grid, that you are giving this flexibility so that the grid will be safe. But how about the perspective of the user? And we're doing that here. And then finally, the application of Parmenides as it is right now is mostly focused on the residential and the DSO perspective of energy communities. But then we also assert that this approach of trade-off exploration, exploitation, analysis, and management are also extendable and applicable to other industries. And I think we have here different industries, and a lot of you here are working on the data center segment and approach that we believe are also applicable in such aspects. So that's it. Thank you very much.
Okay, thank you. Final presentation for this first round of presentations is the Reach project presented by Fabio.
Good morning, everyone. I'm Valeria Palombe, and I'm a researcher at National Council of Research of Italy in an institute called Institute for Advanced Energy Technologies based in Sicily. The Reach project, which has the claim, the fullest call from the cleanest heat, is actually coordinated by my colleague Andrea Frazzica. You will see his contact at the end, but right now they are holding the general assembly of the project, so I'm here representing him to present the project. So, Rewitch is a 4-year project. We are now in month 18, so a little bit like 1/3 of the project. It includes 26 partners from 10 different countries. You see there is a quite large group from Germany and from Italy. Then there's companies from Spain, Poland, Latvia, Finland, and so on. The main aim of Rewitch is to demonstrate up to TRL 7 two different solutions for thermally driven cooling and heating technologies to be used within industrial projects. This is the general scheme of the project. We are now going to analyze this more in detail. So, the two main technologies that are going to be developed are a new generation of adsorption chillers. So they use a solid sorption system that should be less expensive and more compact than what is there on the state of the art, able to be integrated in processes or in a containerized solution, and two new working versions of absorption chillers, so working with liquid solutions that should also be made more flexible in terms of range of operation by including a mechanical compressor. In addition to that, there will be a new or best integration with solar thermal collectors. The solar thermal collectors are being developed by TVP, Swiss-Italian company that is producing flat plate vacuum solar thermal collectors that can be used in a range between 70 and 130 degrees in. Or, of course, integration could be done with waste heat. Then there's PCM-based test system that is being developed by the University of Birmingham. And there are 4 demonstration sites that cover different possibilities. These 4 demonstration sites are a brewery, which is based in Poland. There's a recycled paper industry that is based in Lucca in Italy. There's an agro-food industry which is in Spain, and a biorefinery in Greece. In addition to this, there will be a 3 replication site that will test in kind of open loop computation the solutions for Rewitch. This is the solution on the adsorption chiller for which we are collaborating with absorption technologies to realize it. It is based on a patented solution by absorption technologies, which is a little bit different from the standard systems of this case. I don't know if you are familiar with the absorption systems, but usually the way they're made is that they have a container where you have the heat exchanger with the material, and a container that could be either somehow in the same vacuum chamber or in two different chambers connected by vacuum valves, where you have the condenser and the evaporator. One of the main issues that have been limited historically the power density of this system is the fact that under these conditions, since these systems use mostly water as refrigerant, the condensation and evaporation are quite inefficient. Absorption technology is using a different solution. So there is a container where you have the heat exchanger and the material, and a pore structure where where they spray the liquid refrigerant. The refrigerant then reacts with the material and is either adsorbed or desorbed, and it is sent to a condenser or evaporator tank, and then for the heat exchange with the external sink and source, heat exchangers are used, which are much more efficient. This is the design of the system for the various pilots. You can see that this is for quite large scale, meaning that each module of this one is 50 kilowatt. So this is a 200 kilowatt cooling system, and it was arranged so that it can be realized in a single containerized solution that is shipped, that is pre-assembled absorption technologies site, and is shipped to the industry, and the industry basically just has to connect these water pipes and the electric system, which should improve the let's say acceptance from the industrial sites. Then this is the solution on the absorption system side. I apologize because I don't have all the specific technical knowledge on this. This is being developed by the Technical University of Munich together with BS Nova, which is a company from the Biles Group. It is this is the absorption cycle in which they included a compressor inside to increase the temperature lift. This allows to provide both heating and cooling at the same time, and also to have a better range of operation. The compressor used is similar to the turbo compressors used in automotive industry. That's more or less the derivation, and it was designed by the TU Munich. This is the integration that is done with the Biles BS Nova systems. The compressor is connected on the outside, and there's a system that is used to define the operating pressure level for the compressor. These solutions allows basically very minimal modification to the standard chillers by BS Nova, while increasing a lot the possibilities for the application. Then, regarding the key learnings and recommendations, we saw that for both the adsorption and absorption system, one of the main problems so far that needs to be solved is to find a way to have also a standard or a simplified way for designing them, because we saw that there is a need for careful knowledge of the process where these systems are being integrated and so on, which somehow complicates the use in or the replication across industries. Then it was also seen there was quite a lot of work being done within the project on the industrial stakeholders' acceptance, and we saw that there is all of them asked for proper business models. For example, some kind of ESCOs-like models where chiller and heat pump manufacturers need to have agreements also with the solar thermal system manufacturers if they want to install somehow the entire technology package. And also a lot of industries expressed the desire to have a kind of business model where they could have called as a service. So that's why I was mentioning ESCO-based model. So you could have capex, a zero capex installation, and then the company takes some of the revenue, the companies that install the system could get some revenues out of this. And also that the beam-based engineering that is being developed by IDP is an important added value because it really reduces the risk in problems during installation. And of course, there's quite large replication potential in different industrial sectors. That's it from my side. Then it's time for discussion.
Thank you, Maria. There's about 20 minutes. Maybe you can address questions from the audience. And
so I think we should start by asking if somebody has any question for any of the presenters. So,
Question?
yes.
I can. One question is related to the absorption heat pump, because I have seen that with absorption heat transformer, they place compressor, but in between, let's say that the opposite, so between the evaporator and the absorber, which would be in that case is used to upgrade the heat. And I wanted to know if you know if that's a patent technology by BS Nova or
So
there are any other machines doing
no,
that?
so within the project, the first, let's say, year of the project, they made quite a lot of small-scale tests and at the same time a lot of simulations to find out which was the best placement of the compressor, considering mostly the constraints in the construction of the compressor itself, which was the biggest challenge, because when the proposal was actually written, BS Nova and TU Munich had a discussion with a company called Efficient Energy, if I remember correctly. It was a company from Germany that was selling compression heat pumps using water as a refrigerant. So they were supposed to use their compressors, but this company went bankrupt. So this was not available anymore. So basically they had to rethink a little bit the way they had considered the project. And so at the end, they found out that this is the best solution. And as far as I know, I think they are thinking about patenting the design. Not sure about the cycle itself, but the design of the compressor, I think so.
Okay, thank you.
Maybe next time introduce yourself.
I'm Gianluca Brown from Politecnico di Milan.
Yeah, thank you. I'm Attila Moritz from Heatwise project and HVAC systems. I have a question to you, and then to also the other presenters. So my question to you is this: you have 32 racks and 100 kilowatt per rack. I just missed it, or overall? I'm not sure. Overall, you have 100. Okay.
It was 100. Yeah.
Okay. And then I think it's the first 5 minutes. I'm sorry for that. But this absorption chiller, which is in rack mounted, right? So it is in row, in between racks, right? If I understood, it is inside the rack.
The adsorption chiller, that is the technology that we are developing, it will be integrated in the rack.
In the rack.
Yeah,
Okay.
it will be in the back of the rack, and it will be integrated in the rack.
And the heat transfer is happening between. So you chase out the heat from the rack on the back side into the surrounding. I missed that. Or you deliver it away in the water.
It's integrated, and so it's everything inside the rack. So there was a scheme, and we're working on it. But yeah, the heat it's not going outside. So this is the rack.
Yeah.
And these are the servers. And so at the back of the server, you have the heat. And the heat is, it's get from a heat exchanger that is here on the reactor.
Yeah.
And then it's used for the absorption.
I bet there is this blue is getting in. This is air, right?
Yeah,
cold
this
air.
is then the cold air.
Okay, and cold air goes out. So the heat gets in the lower into the absorption.
Yeah, it's used. Yeah, so we have 3 temperature levels. So the high level, the low level, and the medium level that is here. That is projected then outside. And indeed, in my final slide, I said, okay, we can also recover this medium heat that is around 30 degrees C. While this one is around 60, and this should be around 20.
Okay, so this 60 you bring to the absorption module and you use it to drive.
Yeah.
Okay, so that is the fuel, let's say, of the absorption. Okay, and then you get out practically how much? 30.
30, the medium, they
30 into water.
Yeah.
Okay, and into the servers, because there are this green, here between absorption and the server. What is that? What kind of media?
This is cooled liquid. Sorry, it's water. These servers are
water cooled.
Water cooled.
So they're like on chip. Like on the CPU.
CPU.
It's on the CPU.
It's ready.
Okay. And what is the heat output from one rack? So what is the energy density of one rack and the heat output? Capture.
We are working with rack of 10 kilowatt, which is the target that we have right now. We are working with a specific manufacturer. Now I don't remember the name of who it is, but we are doing everything on a specific rack model.
Very interesting. Thank you very much.
You're welcome. Other questions,
I have
Marco?
also a question for you, or anyway, for those who deal with the server cooling. I think it's high quality and that's it probably. And my question was about liquid cooling, and I just realized that in high quality you also have liquid cooling. So that means that server you have at Politecnico is partly air cooled and partly liquid cooled.
No, unfortunately not. We have 2 pillars. So we have the demo site, that is our server room in Politecnico, and then there is this technology. This technology will not be tested inside our server room because our server room, the server are conventional server air cooled. While for this system you need the water cooled server.
Okay, clear. Are you familiar? Have you become familiar within the project with a little bit with water cooled racks or servers?
Not me. I mean, I'm the responsible of the digital twin part. But I can forward your question.
No, I was just wondering what is your opinion on that, because I see I came across a couple of new solutions, relatively new. For example, A2A, I realized has recently installed for their servers in Asia. They have a French air-cooled, water-cooled system. But also, I found a company in Rome, which is a new co, and they are a startup. Sorry, So I was wondering if you have any idea. Is this a technology that seems to have a great future, or are the limits that high that it's still questionable?
I'm not an expert. I would say, it has a future, because from the heat exchange point of view, it's definitely better to do water cooling instead of air cooling. And I can ask to the audience if somebody wants to add something.
Maybe I can add something, because I was discussing this with some colleagues recently. So the idea is that all the largest producers of servers are going towards liquid cooling, because the power density now, the cooling requirement also is too high for really thinking about efficient air cooling. So I think all of them are moving towards this solution. So for sure, above a certain threshold, Dell, IBM, they are only selling liquid cooled solution right now.
Okay, so it's already an established solution, you think?
For large data center,
For large data
yes.
centers, I think so.
Our is iQLT.
Yeah, it's just a server, yes.
Yeah, but I mean,
Not a server room, so small
Yeah.
data center, while the big one, yeah.
Yeah.
But it's also, immersive cooling, right? You are doing
Yeah.
it, so yeah, what is the capacity of immersive cooling in data center? The range, what is?
Sorry.
The range of the data center where you usually do immersive cooling, I
I
guess.
mean, it's like the scale we're working at is going to be just 1 unit of 40 kilowatts.
Okay.
So the system we developed is actually 1 unit,
Okay.
which is like size of this black box maybe, and it's 40 kilowatts, so we can apply it actually to any size in the end. As many units of that as you want.
for example, to give you an example, in our school, we just brought a rack server which includes 6 high performance computers working either with large CPU and GPUs, and for like just one rack with 6 computers, the cooling demand is almost 8 kilowatt.
How much, sorry?
8 kilowatt, which means that in the end, they actually suggested us to install a chiller for cooling.
Actually,
Because
well,
8 kilowatt still,
It's just small.
yeah.
it's just a small system.
And the power density of servers are increasing drastically. So before I was saying our server room in Politecnico, the electric load was 100 kilowatts for the 32 racks. Not all the racks are full of things inside, but now the high performance computing part, because we have high performance computing, half of it, and the other half for administration server. High performance computing, we are changing the server with this new server with GPU and CPU. And and the electric and the density, the power density is the double or the triple of what before.
So it's increasing.
And so the liquid cooling is more and more needed.
And there will be a thematic track right after lunch about data center, so large data center cooling. But which is a pity because at the same time there will be a very interesting workshop on district heating and cooling.
Which you are not involved in.
But you should attend, but there is this very relevant thematic.
Matteo, the Thunder project. I just wanted, it's very interesting that for me, because we are also working on connecting the district heating. And I said, okay, you could not build or they could not accept the construction of pipeline, right?
The same point.
And it's okay. So fine. I know it costs a lot, and the rest of around. I know 1 kilometer costs a really awful lot of money. But you are going to transport by truck or how does this work? So it is like fuel, right? That you're pouring in the energy, and you are discharging. Does it cost much? You are using electric cars, but CO2.
The idea is to use electric vehicles. So just to drop the emissions. But it on wheels actually is quite not so developed solution, but it exists in some place or in some situations, and so we found this solution as the best alternatives.
Okay. What is the capacity of such a truck? How big is it, and how frequently you have to carry everything?
This is something that we are still investigating. So
some guess.
Not yet clear, but the idea is to have weekly one transportation per week to the data center. So consider that the focus of the project is the development of the thermochemical solution as a seasonal storage. So at the end, we are investing a lot. Also, try to investigate how to do this at the best in terms of transportation, because it's a plan B at the end.
Yeah.
And so, yeah, we have also to address this type of questions also from the officer point of view.
Yeah.
And of course, we are trying to do everything to try to be at least economic and environmental friendly and so on.
Because the building a pipeline has very high capex. This is probably much lower. Yeah, capex, rather it is an OPEX issue. Then
Yeah,
do you
it is
have
a-
some kind of guess data for that? Whether what is the total cost of ownership of one system and the other transportation systems like pipe and?
This is a very good question. I don't have the answer at the moment, but yeah, in any case, we made some calculation and we found it at least feasible from economical perspective, given the short distance between the data center and the distributed network in any case. But the idea is to be flexible, not only to supply the data center, the distributed network, but any other.
Yeah, indeed. So practically, you can have a diverse client
Yes, exactly.
group, not only like one pipe serves one client. Okay,
Exactly.
so
this also a point of interest, regarding the heating wheels, that you don't have only one client, but you may have several clients, and in this case, you can also optimize the costs.
that's very
But
interesting.
if you want to,
Yeah, I would like to speak with you about this.
yeah, but if you want more details,
Yeah,
you can
absolutely.
email
It's
me.
very interesting.
Because I have also.
Matteo, about this, I think in DHE Switch, which is a project where Matteo is also involved in about district heating, I think the Polish case, or the one they would like to bring in, works like that. So it's a district heating on wheels. It's a solution that when I saw it the first time, I was very skeptic, and I am still skeptic, but I haven't looked into it. But there are cases where they are already transferring heat, not all the district. I mean, there is some district heating pipes, but part of the clients are being served through.
Because
trucks.
some clients in some condition, for them it's better to have spot supply of heating instead of direct connection.
Yeah.
Because as you are saying, the capex are lower, and of course for them it's only a matter of OPEX that maybe are higher, but it's sort of a business plan that in some cases is more profitable for Eden Woods.
If I may add to this, because we are working on a low-tier project indeed where there are some partners from the Netherlands, and they also mentioned that in some regions in the Netherlands, or for some mostly industrial users in the Netherlands, they are actually also looking at these solutions, because of course, being the Netherlands a little bit complicated to realize large paving systems. I understand it's a very specific region, but they also were mentioning that for different types of users, they were mentioning the district heating, they were mentioning the industrial heat recovery and use, and also to some extent the electric part, so the energy flexibility to batteries. They were mentioning that they are looking at these on wheels solutions.
What is one charge of a transport? So how many kilowatt hours are they able to transport once?
150, if I remember.
Maybe also follow up. Did you already look into like what kind of materials and what temperature levels you will be using there? Because I guess we have similar challenges, only like your storage is on wheels. And also I saw you work together with the company PCM Products.
Yeah.
Are you using commercial material from them, or also are you looking at the
Are you asking for PCM?
For the PCM, yes.
Yes, as commercial material, and we are trying to match the best PCM temperature according to the temperature coming out from the data center, without using in the scheme you found the heat pump in order to match the PCM temperature, but we are still in the phase to decide which PCM is the best according to the temperature from the data center. That is, of course, low. And yeah, but in case we already foreseen the presence of an heat pump.
Okay.
Matteo?
Yes.
I also have a technical question for you, in case you can answer. So, the system you showed here, this one is an air-based system, or it's water-based. This is like per channel, or?
This is air
So-
channel, and the PCM is hosted.
But I mean, here, so this is a air to water in the channel, or?
This is water to water, so like a hydraulic separator.
Yeah, because here you don't charge your operator.
And then there is here the heat exchanger to use water in order, then to heat or heat up or heat down.
Why do you use
Here,
air?
sorry?
Why do you use air in the water directly?
Where exactly?
I mean, here,
Here?
as far as I understand, all these are water lines,
Yes,
right?
water
So
lines.
why do you have an open system with air for the TCM?
No, because we are testing both the possibility. So to have
Okay,
water,
okay.
this is water
Okay,
circulation,
okay.
enclosed loop, but also air. So this is something that is tested at their facility, and then according to some results, we will see if to use this water exchanger or air
Okay.
that needs another exchange.
Okay.
Okay, good morning to everyone. My name is Marco Fitti from Milan Solution, and I'm the project manager of High-Stock project. Respect to the other thermal storage that we have seen this morning, this approach is more related to services and flexibility that this solution will bring into the building and into the grid. So the High-Stock project started in 2023 and will end at the end of 2026. We have a consortium composed by 18 partners covering all the European countries. The project is coordinated by ARC, and we have a lot of research institutes such as EURAC, KPH, CCNR, SME, and other important players in the European research activities. The main mission for the High-Stock project is the demonstration of 4 innovative concepts based on thermal energy storage, based on TCM and PCM solution. This technology will be used in 4 pilots for demonstrate heating and cooling services, but also the production of domestic hot water. And important things I have anticipated at the beginning, we want to improve the integration with the grids and increase the flexibility by the collaboration with an aggregator that will exploit an open source platform developed by a partner. The objective of the project obviously is to increase the energy density with respect to the state of the art of the thermal energy storages, reduce the capex, that is one of the bottleneck of innovative PCM or TCM solution. To bring the TRL9, we want to enhance installation efforts and create a business model that can be compared to lithium batteries prices and market penetration. Here you can see an example of what we have now. So we have some thermal energy storages integrated at building level and the grid connected to the building. So we don't have a direct connection between thermal energy storage and the grid. The concept that we want to demonstrate and validate is improved connecting the thermal energy storage to the grid. In details, it can be become this picture. This picture represents the flexibility enabled in the buildings and different players that can be included in this value chain. For example, we can have direct connection of grids to the thermal energy storages. We can use an aggregator that can manage the flexibility of the grids. The aggregator can also connect different type of renewable energy systems, such as PV system, solar thermal power, etc. We have a technology that have to control the flexibility into the grid, and we can also integrate consolidated technologies such as heat pumps. Obviously, this approach need to be scheduled because in order to optimize the cost, the prices, the scheduling become fundamental. Here you can see the 4 demo that where we are testing the solution. The first is in Austria, in Landeswang, where we are testing PCM technologies integrated in a heat pump solution developed by Ochsner. We have the second live in lab in Stockholm, in KTH, and here we will also test PCM for heating. We have another important real demo site in Montserrat, Spain, where we want to test the integrated solution, so the TCM unit. So the difference between the 2 modules are more or less related to the so the PCM units will work more or less with a timeline of 1 day of storage. The TCM will cover 1 month of storage capacity. And the last one is the Irish demo site in Dublin, where we want to test the TCM for heating and cooling system. Some results, main outcomes from the project are 4 different configurations for PCM unit. So the first is started the first outcome started with a deep analysis of the market of the PCM in order to select the best material that can be integrated in a high store. We developed a PCM all-in-one unit because integrating this solution in an Ochsner heat pumps. We also analyzed different configurations for low temperature heating and cooling, and another one. So the PCM low temperature will be cooling driven, and the PCM heating solution will be more related to the heating services. So the PCM unit that I said will cover 1 month of storage capacity, and the last outcomes that, from my point of view, is very interesting in order to enable flexibility and is more or less the main difference between the other research is the plug-and-play aggregator developed by Malmström in order to connect the management system to the aggregators. So in details, you can see some picture about the laboratory in CNI, where different kind of PCM materials have been tested. An example of PCM all-in-one solution integrated in heat pumps that have a particular design for increase the efficiency of this PCM unit. Another particular configuration exploiting capillary matrix-based design for PCM modules. And so this is a configuration of the heating solution with the low heating temperature, exploiting the heat pumps connection. And the last one is an example of the number 5 is an example of TCM heating and cooling solution tested in the CNR. In particular way, we use zeolite materials for the thermal capacity. So we encountered different technical problems for and we solved this problem testing different kind of technology for the research. For example, with direct electricity, with other kinds that solution that are tested in the laboratory scheme. The last one is this module that will be produced for commercial scope, enable the flexibility. So this is essentially the hardware that will be integrated in the buildings, and that permit the dialogue with the aggregators and the management of the flexibility at district level. So essentially, that's all for my side.
Thank you, Marco. Next with the Synergy Net project presented by Renato.
Wow, everyone is really good in time, so I'm gonna try to do my best. I give you 2 minutes. Perfect. It's gonna be fun. So, first of all, thanks to everyone for being here. My name is Renato Ruiz. I'm an energy engineer and I'm the coordinator of the project Energy Nets. For those who still did not hear about this project, is about increasing the synergy in different energy networks. So the presentation of today, I try to give a bit more, let's say, emphasis to do of the main topic we're going to talk today. So application of Panda Presumer model to Canavese Demosite. 2 things. Panda Presumer, so some of you already heard about that, but we can go a bit more in detail. And Canavese Demosite, which is one of our demonstrators that gave our first results. But first of all, a short overview about the project. So the Synergy Nets project is composed by 9 work packages, 41 deliverables, 12 milestones. It started in September 2022, and it has a length of 4 years for a total budget of roughly 10 million euros. As all the project of the cluster, of course, is a part of the Horizon 2020 goal. As you can see here, we are pretty well spread in Europe. We are about 19 partners spread among 9 different countries. France, Spain, Sweden, Italy, France, Germany, Austria, Slovenia, and Belgium. Yeah, okay. I got all of them. I hope I didn't forget any of them, but also here, I just try to give a sort of overview how they are spread among research and academia, energy supplier. You will see soon the real goal of the project. So DSO, it's really important. We have 2 DSO in our consortium. On top of that, in our advisory board, for example, we included a TSO, so distribution system operator and transmission system operator, which for our goals is really important. Software provider, of course, association and network. So, well, I would say you still, especially from home, you still did not miss that much. So that's the overview of the project and why I'm saying that TSO, DSO are really important for us. If you look at the objective of the project, what is the main goal for us is to optimize the planning of district heating and cooling. So we're talking about DHC distribution grids with multi-energy system models. So that's why the Panda Presumer, we will go soon to that. And what we want to do with this model, we want to optimize, we want to enhance the flexibility for facilitating, of course, the sector coupling for the services of DSO and TSO, including, of course, also the final users. So basically, I already told you about the Canavese Italian demo site, but it's not the only one. We have in the project three case studies, three demo and 2 case studies. Let's start for the number 1. So Italy, in Milan, here, Canavese. So basically, we have a district heating which is really differentiated because of his size. I will give you some number later, but for us it was, let's say, pretty challenging, of course, to optimize such a huge extended system. So I just introduced to you the demo number 1, so we can go to the demo number 2. That's a demonstrator in the city of Ljubljana, Slovenia. So also in that case, we have a pretty spread area to cover. And what is the goal for the demo 2 is to go and from a 3rd generator to a 4th generator district heating and cooling. We are still talking about pretty high temperatures, but finally the energy efficiency of the total system is gonna gain, of course, some advantage from this change. And then the 3rd demo site is in Paris. The name Iloga Gaete Montparnasse, that's a commercial center. So you can imagine it's kind of a variegated demand, no? Because we have offices, we have we have commercial offices, we have also a hotel. So we have really different type of demand. We have, and what is really important here to highlight, we have a 5th generator district heating, and there are not so many in France, not so many in Europe. So for us was a really innovation and really nice to have the opportunity to develop our models in this plant. And then 2 case studies, basically more for the replicability. So one in Spain in the city of Cordoba, one is Västerås in the city of Sweden. And yes, you can see here basically very a short sum up what we want to represent. Of course, any case study is different, but what we want to offer also to the, let's say, to the community is to have open source application, open source models. And you can see here a bit what we plan to develop, the type of technology and the demo or case study. And let's say the good news is that finally, I talked about Panda Presumer before. So for someone that maybe already heard about that, Panda Presumer is on Pandas. We started from Panda Pipe and Panda Power that were modeling more, like the name says, grid system, power system, and pipelines. But now with Panda Presumer, we can match all together, and we are also working on a easy user interface, which is like also with a sort of drag and drops system, very helpful for the user. And is everything online? Is everything on GitHub? We also had some workshop on it, but you can really find everything online. So I want just maybe to add some more information now on the Canavese plant, since the time is running out, and the goal was to share something that is not online, share something that is not, let's say, public yet, because the Canavese plant has been our first demo case where we run the optimization model. So we actually saw the results of our work. Just a brief introduction. You can see here we have, of course, the electric and heat sides. We have three different, I mean, not different, but three separated CHP. We have 3 gas boiler, 2 heat pumps, thermal storage, and also an electric boiler. And basically, to show you a bit how does it look like, here we have a representation of all the Italian system that is covered by the Canavese plant. It reminds like of GIS representation. And finally here, you have how the platform looks like. So here, it's a bit small, that's why I tried to show you case by case. We had 3 case studies that were primary use case study that we wanted to develop and try to see what's going on and what can we optimize. So first of all, we're working on the long term. So the idea was to try to understand in the long term how much is the availability of flexibility that we can get thanks to our models. Then the second one instead was for the day-ahead mechanism. So the day-ahead, what we were trying to see is, can we activate? If yes, how much flexibility? Because if you remember in the main goal, we are the big word flexibility through the day-ahead mechanism. And finally, more also, let's say, challenging goal, because what we were trying to get, it was to get an additional flexibility in case of congestion. So let's say in case of crisis, let's say, or like unexpected demand, what we are gonna do is try to get some flexibility to cover the demand. And this is how it looks like. And finally, that's my conclusion slide, the key results of the Italian demo. I'm unfortunately not an expert on that, and these are really fresh results, but I were really wishing to bring to the conference today. So what you can see here on in the left is basically, it's very small, but basically this red here is the threshold or the flexibility that we were able to, we were buying, we got. And finally, what we were trying is to try to avoid to go, that the flexibility was going at the peak, sorry, was going over the threshold. Of course, to bind this flexibility has a cost. So we have to find the right ratio between, of course, how much flexibility do I get and how does this flexibility cost to me. And here is a very, very nice results. As you can see here, we have the dark blue curve. That's our prevision. So that's also what we were trying to do. It was to anticipate the market, of course. And the light blue curve is the consuntivo. So it's what actually was consumed. So you can see here that the two curves are, of course, not perfectly exactly the same, but the error that we had here was very, very small, and we were really, really happy with these results. Of course, as I said, it's very fresh results, but as soon as possible, what we are going to do is to create some, some posts for sure in our newsletter. For example, we are going to give more and more detailed results, because this was the first of the 3 demo cases that was giving us the possibility to test our models in winter. There will be the time for the Slovenian and the French demo case. And with this, I would like to thank you, and for question, I guess, later. Thank
you, Renato. Perfect on time. Next is push to it. One Luca. One Luca.
Gianluca.
Gianluca. Yeah. Floor is yours.
Yeah. Thank you. So, good morning. My name is Gianluca Brami. I'm a PhD student at Politecnico di Milano. And together with my colleague, we are working on this project, European project named Push to It. So it's not really involved into cooling solutions, but there are many topics that are directly linked with what we have seen today. So the objective of Push to It is to demonstrate the integration of different heat upgrade technologies in industrial context. And the motivation for that is that the process heat utilized by the industry, the European industry, a lot of it, so a huge part, is heat below 200 degrees. And at the same time, there is huge availability of waste heat coming from the industry. So the idea would be to adopt technologies that are able to upgrade the waste heat and utilize it into process heat. So the objectives are to develop and optimize 4 different heat upgrade technologies, and then also to develop business models that are able to push forward the market potential of these technologies. On the bottom, you can see we are also many different partners from all around Europe. And as I said, Push to It has 4 different heat upgrade technologies that will be installed in 3 demo sites. Here, just a small overview, then we're going to see the demo sites more in details. So demo 1 is installed in Germany, then demo 2 and 3 are installed in the same place here in Italy, and demo 4 instead is installed in Belgium. Now we're talking about the demo sites. So demo 1, as I said, in Germany, it's paper mill in Weissenborn. And the technology here is a vapor compression heat pump that will recover heat from the paper machine dryer, so around 700 kilowatt of heat, and it will upgrade the heat generating steam at a pressure of 2.3 bar with a COP, electrical COP of 2.3. You can see here a timeline of the installation. So now the machine has been manufactured and it has been integrated into the demo site. And actually we are receiving the first data in these days. So we will see more in the next months. And on the bottom, represent an image of the RIA technology and of the demo site. Regarding demo 2 and 3, these also are installed in a paper mill that is in Guarcino, so close to Rome. And the two technologies are, again, a vapor compression heat pump, but this time coupled with a vapor recompression and an absorption heat transformer. Both technology will receive in input heat coming from the cooling water of a cogeneration plant that is installed close to the paper mill. And in case of the heat pump, this will upgrade the heat again in the form of steam, and then this steam will be recompressed with the recompressor. And for the absorption transformer, the same thing, but in this case, vapor will be recompressed through a thermocompressor. And the status of these two technologies is that the heat pump has been manufactured and is going to be integrated at the end of this month, while the absorption transformer has already been installed in the demo site and is going to be commissioned pretty soon. Last demo site is demo 4. This is installed in Antwerp in Belgium, and in this case the industry is a chemical industry, and the technology is a thermochemical heat transformer. The heat that it will receive comes from an exothermic reactor, and again the heat will be recovered by the thermochemical heat transformer and reintroduced in the process as steam. This technology has already been installed and it's actually right now being monitored and optimized for the demo site. So other than developing the technologies and installing them in the demo site, we have to monitor them. So we have developed a common monitoring protocol across all the demo sites. And the system is now being installed, and the objective of that is to give evidence of the performance of the heat-upgraded technologies and to be able to compare them in the different demo sites. And moreover, what we are doing right now is developing a continuous model assist monitoring, meaning that there will be models of these machines that will be able to compare the KPIs calculated with the model to the ones that are to the actual KPIs. So you will compare these two and provide feedbacks on the operation of the machines. And last two slides is that other than developing the technologies and developing this monitoring protocol, an important thing is also to disseminate awareness about heat upgrade technologies. So there is a huge part of the project is developed to, again, dissemination. And in that field, we are doing replication studies, meaning that this technology will be modeled and then replicated in different industries or other sectors. For example, here is a case studies that University of Valencia has been doing about district heating. It's a real case in Italy, so in Lombardy. And this system right now is producing around 60,000 kilograms hour of hot water at 110 degrees, which are produced by boiler and cogeneration plant. But there's a chemical industry close to the district heating, which has around 8 megawatt of waste heat in the form of pressurized water at 33 degrees. So the idea is to install a heat pump to recover this heat and replace the gas boiler. And the heat pump, since there's a very high lift from 30 degrees to more than 100, was modeled in the EES, which is a similar software, and it was a double stage compression heat pump plus vapor compressor, again for the high lift. And the results of that is that depending on the availability of waste heat, because we have in the, let's say, normal scenario, the availability is just for 7,000 hours per year. In this case, the heat pump would provide savings for around 300,000 euros per year. And depending on the amount of piping that is needed for the installation, you would have different payback times. So since piping is a high cost, with 4 kilometers of piping, then the payback would be 15 years, more or less. With 1 kilometer instead, it would be much less, so 7.4 years. If we thought about increasing the availability of waste heat to for the whole year, of course, the operational savings will increase and the payback time would decrease. With 4 kilometers of piping, we would have just 12 years. With 1 kilometers, around 6 years. And these kind of studies have been done not only in district heating, but also in other industries. So to conclude, let's say that probably the most interesting result will arrive in the coming years, since we will be monitoring the technologies and we will see the impact on that they would have. But so far, we can say that high temperature heat pumps that are able to generate steam at 150, 160 degrees are actually available. And the feasibility of installing them is not actually the technologies, but it depends really on the demo set. So one really has to see if waste heat is available, what's the energy demand of the plant, and some installation constraints that we also faced during the first part of the project. And with the replication studies, we demonstrated that potential energy and CO2 savings can be achieved with decent payback time. And also that these technologies can be applied to many different industries and sectors. So that's all.
Thank you, Veronica. Next, we have the SEEDS project, presented by colleague from Artron 4.
So, good morning, everyone. So, I will gonna present you the SEEDS project. I am Anaïs Gandolin. I am the Communication and Graphic Design Manager at R2M Solutions France. And I'm also the SEEDS Work Package 8 leader, which focuses on dissemination, communication, and stakeholder outreach. And so SEEDS is a large-scale European project that started on January 1st, 2024, and that will run for 4 years. Our ambition is to develop renewable-based smart heating and cooling systems, and that can tackle the challenging of cooling and heating system in Europe. So, to do this, we are a large consortium with 25 partners from 8 countries, and we are deploying solutions in 6 pilot sites. They are located in Denmark, Belgium, Slovenia, Hungary, and Greece. So we have 5 countries, but we have 2 pilots in Belgium. And in addition, we also have follower sites in Ukraine, and also partners coming from France and also Italy. So each pilot site involves at least 2 or 3 partners, forming a strong local ecosystem that ensure the solutions are well adapted in a real context. And at this stage, so we are in 2025, and all 6 pilots are in the phase of constructions, installations, and also initial data collection. And of course, the progress differs between each site. And I will now go on into some details. So this is our 6 demo sites. The first two actually, are in Belgium, located in Bruges. So we have 2 pilot sites focusing on heritage houses that you can see here. So one of the sites has already a smart heat pump controller, heat pump system, combined with MPC, model predictive controller. And this solution will be replicated in neighbor historic districts. So this is this one, the white one. And showing how seeds can scale in real urban environments. Next, in Hungary, the pilot is an old apartment block where renovation is really crucial for energy efficiency. So actually, I was there yesterday in Budapest, and we visited the pilot site. And so the building facade is being retrofitted with insulation, and windows are already been replaced, because before it was like wooden windows. And so building integrated photovoltaics will also be installed to reduce demand and also integrate renewable electricity on site. So next we have the Greek pilot, which is a student dormitory on an university campus. So 20 rooms are already equipped with sensors, and a full data infrastructure has also been deployed. And the building is supplied by a multi-source renewable heat pump that integrates both geothermal and solar. And here the aim is to optimize the use of these energy sources while improving indoor comfort and demonstrating flexibility. So that's all for the Greek pilot. And after we have also the Danish pilot here. So the pilot is the only new building in SID. Construction was completed earlier this year, and since July, the building has been in use with tenants that are already occupying the space. And so this is a modern building, office building, equipped with a state-of-the-art BMS, so building management system. And this allows us to implement advanced control strategy for heating and cooling, and to test demand-side flexibility by responding to variability electricity prices. So on the district heating side, our partner DTU has developed a method to design variable heating prices, which will be tested now in this building. So they are also in dialogue with the local district heating company to explore implementation of dynamic heating tariff at scale. So in Slovenia, the pilot involves 5 petrol stations that are owned by Petrol, the company, and these stations are integrated into the portfolio of a flexibility provider. So the idea is that flexibility from this small distributed asset can be aggregated and then traded on the electricity market. So the main focus of this pilot is to develop the automation system architecture and trading platform to make this possible. Okay, so now let me give you an example of how SIDS works in practice with the Danish pilot site. So as you can see here, the building is owned by Dundee Business Park, and then Nordomatic provides the BMS. And you can also see here data from the building are collected by Center Denmark. So they collect the data on their platform. And the researcher here and technology providers can use this data to develop forecasting and control algorithms. So here, and once ready, these algorithms are implemented back into the BMS, closing the loop and improving also system performance in real time. So to give you a sense of scale, the Danish building has 5,000 square meters of floor space and also over 1,000 measurement points and data collected every single minute. So data collection started in July, as I was saying, and it already provides a rich basis for testing innovative control solutions. So to summarize, SEED is demonstrating renewable electrifying heating and cooling solutions across a wide variety of building types. So we have heritage houses, cooling solutions, heritage houses, dormitories, office buildings also, apartment blocks, and also 5 petrol stations. So the diversity of the sites allows us to prove that the solutions are both replicable and also scalable, supporting Europe's goal for energy efficiency, decarbonization, and flexibility. Yes, and that's all.
Thank you, Annie. And the last but not least project, Heatwise, presented by Attila.
Yeah. Thank you. Hi, everyone here in the room and also online. So my name is Attila Moroz. I'm representing here the Heatwise project and also H1 Systems, which is Hungary's leading data center design, build and operate company. And we are an integrator company. So we are bringing together solutions that we put together and bring to the market, sell to the client. So I was very happy listening to your presentation and learning about TCM, about digital twin, and many other technologies. But let's see what our project is doing. So heat marriage, thermal marriage of data centers and buildings. And we have, what is a data center doing? It is consuming electricity and converting it into data, and there is a byproduct, heat. And this heat has to be rejected, otherwise the IT gets cooled. So there is a cold needed, and then heat is ejected. Buildings, they need heat all year round, so obviously we can give the heat of the data center to the building, and maybe the building can give cooling to the data center. We have 3 key KPIs here: PUE, ERF, PES, power utilization, effectiveness, energy reuse factor, and primary energy saving. So why they are important? You see that this is how we are measuring ourselves to others. So PUE is the best or most commonly used KPI in the data center. So if 1, it means you are not spending energy on cooling. That will be great. Everyone, all operators are happy. You are spending energy only on IT, but this is not the case. The average is, European average, 1.6. So what we are showing here, we are able to jump down 1 order of magnitude. This is a big jump. There was a high school, or I don't know who said 1.1, so try to beat you. 95% means we capture almost all, with some losses, all heat generated by the IT. Now, everything is rejected. Mainstream, I'm talking about, not about you and the other project. And PES, okay, primary energy saving, which is a massive decarbonization goal. So, but how do we come from what is the context around and what is the challenge? So there are digitalization, energy sovereignty, and climate change. These are all social pressures that are demanding that the industry is changing, meaning the data center industry, the energy density of the racks of the data centers is increasing. So what does it mean? How much IT you are able to fit into one rack? Average now is 5, 6, we are building 10, 12. In high performance computing, we are around 100, and probably the mainstream will be soon around 50, 70, 100 kilowatt per rack, so in one cupboard, okay? So it is a huge jump. Who is able to cope with that? Buildings, they are providing shelter and comfort. This is their primary aim. But they are pushed by all the social challenges to do something to reduce energy consumption, to contribute to the CO2 reduction, and already targets are set for all of them. So the data centers in Germany, in France, in Spain, there are already such targets for waste heat that we have to think how to comply with that. So, but let's see, because what is the problem? What is the core? We believe the core is the cooling of the data centers. And what's the problem with the current mainstream? So what is happening actually? Air-cooled. All kinds of air cooling devices are on the market. They are using split klima, sear, crack, whatsoever, big machinery, smaller. Anyhow, air is used, and usually around 1832 degrees cold air is blown into the data center, and then around 25, 35 degrees is blown out into the environment. So the problem is machinery is big, air is a very ineffective heat carrier, energy carrier. There are problems already during the summer heat waves. 40 degrees outside, you have to do some compression, machine using to create this 18 degrees out of the 40 degrees outside. Then there is limited data which is governing the cooling. So practically free data, humidity, cold air temperature, and the amount of the air blown through. So what is happening? We are wasting the energy. It is going into the liter, let's say. And actually, we don't really know what is happening inside the rack, in the server. So our CPU or GPU is maybe working hard and sweating and cold, and sometimes it is too cold, it's trembling. So because we are measuring this here. So like imagine the room temperature, how you feel like here is measured in the room over there. So kind of nonsense, no? Okay, so what we do? Obviously, I just told to you. We look at each component, CPU, GPU, hardware, memory, motherboard. How do you feel like? Can I measure you? Okay, so this is the story. And we blow with them. We cool air, we give them liquid cooling, okay, and everyone gets what he needs. So liquid cooling for CPU and GPU, air cooling for the rest, the auxiliary stuff. And then we are collecting all this and give over high temperature heat to the building, and higher than I showed you in the preview, so higher than 35, because we will see in the buildings 35 is not so good. 55, is at least needed, or 60. If I'm talking about domestic hot water, but even at the low temperature heating, that is kind of enough. So how do we get there? We get there that we collect data in each and every stage, on each and every component. A lot of data also about the building. So we need a data management platform for that and all kind of optimization tools. But before I would get there, what is our value proposal? So we give higher performance. So throttling, this is one of the key problems of the data centers. So when it is too hot, then they are bringing down the compute, and we are waiting that the CPU gets back to the proper temperature. So we say 95% is IT utilization. This is huge. This is dropping a lot the capex of the ROI of the investor. Now it is, if you nowadays 60, 70, is the IT utilization is good. We keep out very high temperature, 40, 45, 65 degrees. That is great for a building already. All this we do without additional heat pump, additional absorption chiller, no compressor work. So that is good for the business, less capex, and we believe very good OpEx. We can go up to 100 kilowatt per rack. That is our future. Now we are testing around 20 kilowatt. You can comply with the reporting that the policy puts on you, report on all the KPIs that are demanded, and what I mentioned, you contribute, you become green. You can talk about that. So where do we come from? We come from 8 countries. We have 5 pilots. 2 very important pilots we have where all the novelties are implementing. This is in Sweden, in South Sweden, and here in Switzerland. The other countries we have benchmark pilots where analytical tools we are deploying. I don't want to spend much time on this, but we have a history. Yeah? So we started thinking how to become more efficient already 10 years ago, and then we did the Boden type DC. We were focusing very much on the building and how the air is running around. We reached PUE 102. Okay, so then we focused on zonal heating. We get to the rack level, and now we are getting to the inside the server and connecting with the building. So we have novel methods for analytics and planning. Okay, hybrid air and liquid cooling. Liquid is not water. Okay, it's a dielectric phase-changing material. Dielectric meaning you can pour it on your computer and nothing happens. No, and not electrically connected. Building control, we are developing a holistic cooling control for the data center, so handling a lot of data, and the marriage strategy. So how this is going to work together, one and the other. Both of them are independent. They say, my needs are most important. And finally, without business, someone already mentioned, this is one of the most important. Is it going to be ready to be taken up by the market? Is it going to pay back ever? So analytics, we developed analytical method how to estimate the heat potential or waste heat absorption potential of a building, and what is the potential that this building is able to store energy, and what is its flexibility. Okay. Then we put next to it a metering strategy, where to meter, what to measure, data. Yeah, and it matters where to measure. So one of the key findings is, okay, measure not too many places, but in enough places. It is not the really important what is the mains temperature, but what is the system, so HVAC or your heating, and try to connect there, where the temperatures are lower. Yeah, the mains is always the highest temperature. So if you want to learn about this more, I very much encourage you to follow us on LinkedIn, get to our November lecture on this topic, and also further trainings. So you will get informed about that. Now comes planning. We developed open source CFD tool, because the first thing is not to implement this whole package at once and at first, but let's see how you can improve that what is already there. With CFD open source simulation, we have several results of that. You can read more on the website, how to do in simulation without trying anything in reality. And that is probably the most important. And here I will try to wrap up. So how the system is working, we have closed cabinet. Okay. Here inside there is a radiator which is taking up the air heat. It is conveyed into the HRU, heat rejection unit, which is preheating here the cold. Cold is 65 degrees. So with 65 degrees we are cooling the CPU on chip, which is sending back 70 degree vapor, and after some loss 65 we are able to give out to the building, and the building gives us back 45 degrees. So we are cooling with 45 degrees, not with 18. Okay, this is a serial, and we have also a parallel connection. 70% is captured by direct on chip, and around 30% of the total heat by the air component. Control and optimization follow us. Digital twin and heat demand forecast. Mota, probably that is interesting. You can increase the heat in your data center without compromising on other. Okay, that's the point. If I know where to allocate the heat within the rack, I'm able to produce more heat, or I'm able to produce less heat, or lower temperature, or higher temperature. I'm able to set this to the demand of the building. So we are looking what the building is needing. And then last, I wanted to ask a question, really, 1 more minute, last page, okay? Or not. How you are going to make this marriage. So is there a hierarchy between building and data center? What do you think should be? Or not? Before, yes, everyone said building is the king. And then came the data center. No, the data center is the king. So there is no king, there is king and queen, and they are all independently able to work, able to deliver to their promises, but they have to work together. And probably this is the most important right now. This is where our thinking is. how to coordinate this between them. And this is the VHUR. This is a new KPI which we are presenting to you. Maybe you will criticize. It's a waste heat utilization restrictor, and along which we have several strategies. It is a 6-step calculation algorithm, and we believe this is going to tell to them, to the entities, when to produce at what temperature, how much. Follow us on the website, sign up to the KPI, and then later in 2026, we are going to come out with some guidance documents on 6 use cases, how to implement our solution, which is, we believe, scalable from 500 kilowatt. In 100 kilowatt quantums, we can fit at up to megawatt, 10 megawatt size. So that is the last page. Thank you very much. Listen to me. I was the last, but hopefully I was able to keep up your attention, and I'm looking forward to getting your questions here or online. Thank you, Sandra.
Thank you, Vela. I think it's very interesting. So very good to have a few more minutes. We have about roughly half an hour for discussion. I would suggest first address questions from the last 5 speakers, and afterwards we can broaden the discussion with whatever comes up.
Questions for the speakers? Any questions on the online?
Yeah. Sander, how does the online?
We didn't check.
I didn't give
questions.
I didn't give any instructions about the online part. So I'm not even sure.
Me too. Start chatting. No, there is no. I don't see questions.
I don't know if it's enabled.
Should be in the middle.
No, they told me it was just a physical session only.
Okay. Okay. Almost everyone, half of the room is sitting, but sadly.
Yeah, I have a question for you. I'm not sure I understood it perfectly. You were talking about exploiting the building. Were you referring to its thermal mass? Is that what you were meaning?
This is the direction where we are going, yeah, to checking whether we can use the building as a storage. Yeah? So start cooling or heating later, or putting more heat into the building when it is needed. Yeah.
And so have you already initiated a discussion on that? For me, I know this topic from district heating, but it's a very relevant topic in general. What I understood in the past is that this poses especially social issues, also to some extent legal issues, because in Milano, for example, in Italy, for example, we have strict hours when it is allowed to heat or not. But also social issues, because people expect the radiator to be hot at a certain when they are awake and not while they sleep, etc. So where are we in this process? What is your insight on that?
Yeah, we are looking at the standards and regulations, what we have to comply with, and maybe we are going to challenge them. So already we have a few, for example, ASHRAE standards. They said clearly what is the humidity, what is the temperature, what should be provided to the data center. We say, no, we don't care, because we care about the CPU and not about the temperature of the air. Okay, so we are going to challenge these kind of regulations, policies. We look through what could be impacting or what could be the barrier for us, and in 2026 we are going to come up with some solutions, not but recommendations. Yeah.
This is kind of deliverable of the project?
Yeah, absolutely.
Okay, that's interesting. Yeah. Okay, so I'll ask the question next year.
Again, very good.
Get prepared. Thank you.
What you said before about the temperature level, just to add that actually for all buildings, we need 55, 60 degrees C. But for new buildings, even 35 would be enough if you have floor heating. So This one point, and the other. So, what is your technology? I saw the rack integrated system.
Yeah, okay. So this is the key element is an on-chip cooling, and it is based on phase changing. So practically, this phase changing material is boiling in this cold plate, which is attached to the CPU and the GPU. Okay, the boiling temperature is at 70 degrees. It is a very clever solution because there is no hot spot on the silicon, so it is evenly cooling it. That's why we are able to reach this 95% utilization rate. This is going into as it called, not evaporator, opposite, condenser, into a condenser where the heat is then taken out, rejected into the whatever system. Okay, so building, tertiary building we are talking about here in our proposal project, not residential. So we have industry, we have high performance computing, we have offices, this type, hospital. And then the cold, we can set how cold it should be. 45 degrees, the coldness, we can already, help me out again, condensate our steam back into liquid form. And this is only the CPU and GPU. They are the two biggest heat generators. The rest, the auxiliary, is not that sensitive to heat. For example, memory can resist at much higher temperatures. So also the air can be much hotter. Not again 30 degrees, but we can cool with 50 degrees air. That's pretty good. And back to this, we have two solutions. So because we have also very modern building, so just renovation rate in Europe is, okay, you're smiling. So retrofit is absolutely there. We cannot make everything new and 25 degrees heating. But we have also the Swiss pilot. We have their three temperature levels. Then we have their 18, 25 degree, and 60 degree. So also there is another, not what I've shown you, another solution where we are parallel. Systems are rejecting the heat from the rack. So we can serve these three independent systems of the building, three temperature levels.
Nice.
And who is the owner of this two-phase?
Two-phase is Zutacor. That is an Israeli startup company. Zutacor. Okay, this is a startup company. They are pretty advanced with what they have, and our task is to integrate it into this big system and see what are the boundaries of their system.
Can you steer the phase change temperature of the dielectric fluid? I guess it needs to be pressurized to.
It is pressurized, and we are steering by pressure.
Other questions for the other projects, maybe?
I have a question for Panda Prosumer.
Yes.
Usually the open source libraries, they face some maintenance issues later on, like in the project plans after a certain time, no one answers to the questions. So do you have any plans in this regard that are incorporated in your project to address this potential issue in the future?
Well, it's a good question, long-term question, I would say. So finally, as I said in the presentation, we started already. There was a Unikassel University in Germany that was already developing the Panda pipe and the Panda power. So finally, to answer a bit retrofitting this question, we are continuing. So Panda Prosumer is already the next generation. And for example, I mean, as long as the project is alive, for sure, we are always continuing. Indeed, we had a release already, and we will have a second release now because, of course, with Movadel, you can every time you can improve, you can find bugs, mistakes, and so on. So there will be also a second release. If you really ask me what will happen after the project, well, that's always a question of community, I would say. From our side, what we are trying to do is, for example, to make to track everything we are doing. So there is a manual for the user, what we have done, so you can find all the code that has been written, why, how, and so on. Plus, we had this workshop, so we had like really, there is also in YouTube like 3 videos just explaining exactly what's going on. And on top of it, with using like a UX UI designer, we are really trying to also through like really pick and drop and drag to make it as easy as possible. So for in order to kind of incentivize everyone, and at the same time, if the more people are using it, the more it's likely that it's continue to be alive. Exactly. So that's what from our side we are trying. Of course, we cannot guarantee from today up to 2050 that it's gonna still be working 100%. But the idea is, of course, to further and further improve and include always more and more libraries, people, models acting together. That's also, I mean, the final goal of public funded project. No, that's why we wanted to go to the open source.
Thank you.
Welcome.
I just have a question regarding push to it. Because I saw that you are working with and with BS Nova systems. In your project, they are working, of course, as heat transformers, but they are purely, let's say, they only have the thermal compressor, they don't have the turbo compressor, right? Or do they have
thermal compressor.
just thermal?
Yeah.
I also have a question for you, Renato, and about your demo site. I was curious to know if it is the results that you've shown are in simulation or in real environment. And so how are you dealing with flexibility in the Italian context, that the flexibility market is not yet ready?
It's really, really complex. Indeed, the results that I show you, I mean, first of all, the results that I show you are from the real world, let's say. So it's not, I mean, yeah, there was the line simulated, but then there was also the real results, the real data. On top of it, what we have done, and it was pretty, let's say, complex process during this, I mean, before the summer, all the models were ready, everything was already installed. And what we asked was really to get the control of the Canavese. So which is not everything that, not something that you can do every time. Indeed, we were also thinking to make a longer test, but at the beginning we just booked few weeks in July and August, because it was like in summer is when you have the highest degree, let's say, of flexibility. So you have more possibility to play a bit with it. But how do we in the future will interact with the whole, let's say, system? It's still not that clear.
No, you answered to my question. Can I ask you something more?
Yeah, sure.
And so, which type of approach did you use for optimization? And then, what about you said that you are testing in real cases? So, which type of components, hardware, did you have to install?
Yes, it's getting very technical.
No. Just to say, if you need to install new hardware, or maybe you interacted already with the hardware that they had, and which type of component or equipment are you controlling, or did you control?
I mean, the one that I show you especially for the Canavese, I can tell you because it was a real practice. All of them were under control of us. So we had from the heat power, the storage, the e-boiler, and so on. For the question of additional hardware, I have to ask, to be honest, because I took over the project after 1.5 years, so I don't know how much, what was there at the beginning, but for sure I can try to ask and to answer you. Yeah.
Other question, curiosities?
I'm wondering how your digital twin is working. What kind of approach do you have there? Is it model-based? Is it data-based?
Yeah, it's but we have mainly physics-based model
but in the end we have a gray box model.
Okay.
So yeah, mixture of the two. For the SimBots, for the simulation model tracking system. So yeah, gray box model.
Okay.
We try to keep it simple, but without losing the physics behind, and in this way we avoid the long training period needed. While the MPC is based on a black box model. So IMP from Serbia, they are using as reduced order model for the MPC, a black box model, and so yeah, they need data to train the model. So this is our approach. And for the digital twin, we are using in order to create the SimBots, we are using different softwares. The main one is called EcoSim Pro, and Pablo Legazpi from BDTA is working on it. Is the leader with Paula, that is outside of the BDTA stand. While in Polyme, we are working a lot on the chiller, this large chiller modeling from Schneider, from Uniflare of Schneider. And there we are using also other approaches. For example, we use a lot of Modelica and the FMU standard to create object and to be interoperable. And Marcello Aprile, that will be here in the afternoon in the auditorium, he does model in Fortran, and can as well create FMU, etc. And in the project,
Chiller is also done in Modelica with the
Yeah.
FMU.
Yeah.
We did it.
Yes, CNR did it, are working on it for the Sorge thermal-driven system. So yeah, these are our tools. And then IDP is a Spain engineering firm. They are the leader of the overall framework of the middleware. So they host the digital twin, where we have these different layers. So with these inputs coming from different partners, we have already the page of the software, and now we are fixing all issues, let's say. So yeah, soon it will be ready, and I hope also to be public. Yeah.
Okay, again.
Yeah, when I hope.
I would be very interested to learn from you. You solve this.
Yeah. I hope. During early next year.
Next year. Okay. This is really fun. Thank you.
Other questions? Okay. I saw that a lot of us are working on the exploitation of the building thermal capacity. And I think it's tricky. I think that what Marco said, it's a very good point. As researcher, we say, okay, we can exploit the building thermal mass, but then you have to deal with the regulation and with the occupant, because I saw before your violin, it was in a good range, just 19, 21, maximum 22. So it's good. Sometimes I see some paper where they say, okay, I can increase the air temperature up to 23, 24. Maybe it's too much in winter to do it. And about regulation, I hope that when you say that you are using, let's say, preheat, or any way you are doing it in order to use electricity with the lower CO2 equivalent content, I hope that we will say it's okay. I mean, the regulation says that in Milan you can have 20 plus 2 maximum temperature inside, but this is linked to the fact that historically we are using fossil fuels to heat up the building. So I hope that there will be regulation that allow you to.
I think it requires a regulation change anyway, because no commercial operator would probably, maybe some would, but in principle you don't want to break rules. So I think the discrepancy is between what makes sense and what all the regulations allow for. So that requires some change. I agree with you. It should not be a problem, but it's just a typical time related to change regulations. And that's why I was interested understanding if anything is moving, changing in other countries. Maybe I don't think it is in Italy. But
No, I didn't. I heard a lot about dynamic electricity tariff. We are talking a lot about it, and also in Italy soon we will have it. Right now we have some pilot sites where they are trying to do some aggregation project, like Mindflex is one. There are others in Italy where we are trying to do flexibility on the electric grid. But yeah, about what you said about the comfort of the person, yeah, it's another topic, but it's time to discuss. And then I was very interested by your project with all the PCM storages. So yeah, the building can, in the building you can exploit the thermal mass, but you can also add a lot of storages that you can use. And yeah, I think that there is that this is the future. We saw in Spain, they had a big issue in May with yeah, the whole electric grid yeah, go down. So yeah, I see a lot to do for us, and I saw that a lot of us are working on it. So I saw very promising results.
But also, for example, in our storage aggregator, we are already testing it in Spain, because in all the other countries we can do it. Also in Spain, they can only do it, we will not do it, let's say, on the real grid. It's because they have their own local layers, and we'll do it with local storage and transmission cabling, not towards the external electric grid, because this is not how it is in Spain at the moment. So there are solutions, but as Marco was saying, there is a layer missing.
Based on what you said earlier, I wanted to also just add a remark on the range of acceptable deviation when responding to a flexibility request. One thing that I did not mention earlier as well was that maintaining that particular range of discomfort or deviation, which is acceptable, also meant that at least particular case, we're only able to respond to around 20 to 30% of flexibility requests. And I think the common premise when there's flexibility research is responding to each and every flexibility request and maximize how much flexibility can be given by a certain building or a certain facility. So perhaps a question to anyone who could answer is that in different projects that deal with flexibility, what is a typical expectation? Is it to actually coming from a premise of responding to all flexibility requests to as much as possible? Or are there certain best practices that, okay, responding to at least 10% or 20% would be okay? Does anyone have thoughts on that?
I would ask you, yeah, how do you find the flexibility request? Because yeah, I do study on flexibility. Usually I go the other way around. So I tell to the electric grid manager, okay, this is the flexibility that I can provide you in this period.
Mm-hmm. Yes, so I think that also uncovers still another gap in flexibility activation, which is even like what kinds of signals are being sent to the flexibility providers. Because in our project, I'm using the USEF Universal Smart Energy Framework messaging protocol, which gives certain range of allowable loads at every time unit. Like for every hour, these are the available loads, and then we can tell if the facility can give that amount or not. Whereas I think the other way around is like offering, this is how much I can give you. And it's the grid that says accepts or not. So yeah, I think that's good to think about because there's no single approach yet, I suppose.
But Enzo, I think the way I understand it, I'm not an expert on flexibility, honestly, but I had to follow a bit the bridge working group because of Parmenides, but also Heister, etc. So the way I understand it is that flexibility nowadays, but even some years ago, works as Rossano was mentioning, me as a company, let's say, we're not talking about the single users now, but as an operator, I tell you you are the DSO, I tell you in advance how many megawatts or whatever I can offer, then it's my responsibility to have them ready at the time I decide. So I think the exploitable ratio is 100% if that's what you meant. Now, what you're doing in Parmenides, I understand from the project, is you're trying to make it automatize it and also distribute it among many small users. And that's a level that I'm not sure is yet existing in the commercial way. That requires sending signals, and that's without a predefined schedule across the day and across the week. But nowadays it is like the DSO knows that Polytechnico, okay, it's not good, but can
as
offer
a large facility.
Yeah, as a large facility, 3 megawatts for 3 hours on Monday and from 4 to 7 p.m. You know, I think that's how it is.
I know for sure, I mean, at least in Italy, there is no commercial way to do this. That some of our colleagues work on the electric side. They have a project ongoing with Enea, and they are trying to do something similar to your projects. If you want, you can drop me an email and also put them in contact with them. Basically, what they're trying to do is exactly like this. So, in this case, the large facility says, okay, have this. Then within, of course, you can do this only if you have multiple storages or something that in your system allows you to have quite large flexibility. And then what they're trying to do is to somehow put together all the signals from, in this case, it's 6 different buildings, if I remember correctly, and to operate the heat pumps and storages that are within the grids to guarantee the 100%, so guarantee everything you were telling to the DSO while keeping the comfort level on this side. The main issues they saw is that you can only actually do this if some of either you have very large storage capacity, which is usually not economically profitable, or if a large part of your facility includes non-residential or non-office buildings. So you can play with places where there is no real big comfort issue.
I'll get the project later.